Good morning, I'm Zhou Yang from Huazhong University of Science and Technology, and it's my great honor to be here to present our papers, an active SEM-supervised learning method for distant field prediction, and this work is supported by the National Natural Science Foundation of China. Nowadays, distant field has become a common event, and about 18% of system breakdown are caused by hard distant field in the data center. Over the past decades, in order to solve this problem, almost all methods are limited to offline supervised learning. That means we need to prepare a large amount of label data and need to retrain to accommodate the new dataset. But in fact, a large number of unlabeled data may be available in reality, and the model's data center is complex environment, so it's hard to meet the needs of supervised learning. Before introducing our method, our background knowledge is necessary. The first one is distant field prediction. Our goal is to predict a minimum distant field or a collection of disks in production based on smart statistics. SMART is the widely adopted distant monitoring tool for collecting performance and reliability status of a disk. The second is active learning. In the field of machine learning, active learning is proposed to optimize the classification model by reducing the training set and the labeling cost as much as possible. To enable the model to select sample intelligence for learning, we consider using active learning algorithm. The active learning algorithm selects the best sample by some strategy from the sample pool and add this sample to the training set of the models so that the training classifier can obtain strong generation ability. The last one is semi-supervised learning. Semi-supervised learning is a mature and widely used machine learning paradigm. The key to semi-supervised learning is how to use a large amount of cheaper unlabeled data to improve the performance of the classifier. Our analysis built on 4 smart datasets collected from Backplane and Baidu. The Backplane data used in our paper totals 54 months from 2016 to the first half of 2020, which is the largest and most recent data currently in the Backplane. Baidu dataset contains only one disk model, and its record had been processed and is only used as a supplemental to the experiment in the paper. We talk about active learning, so why do we use active learning? Typically, the distant field rate follows the beta curve. In the entire life cycle of the disk, the steady state will dominate, and the sample collected at this stage are very similar, so there is a lot of redundancy. In order to investigate whether there are more redundancy samples in the backplane dataset, and whether active learning can obtain similar results with fewer samples in the case of a limited training set, we conduct the following experiment. Figure shows an experiment using active learning algorithm on the DIG1, DIG2, and DIG3 datasets, which are divided into training and testing sets randomly. The experiment shows that due to the small number of training sets, the prediction effect of the models is poor. However, as active learning continues to select valuable samples, the training set keeps increasing, which makes the prediction ability of training models significantly improved. And finally, tend to be stable. The last sample add contribution less or even have a negative impact on the classifier. This phenomenon further validates our suppose that small data on the disk is not only redundant, but sometimes has a negative effect on prediction. Most of the current research on distant field prediction using supervised learning, and all the samples need to have clear labeled value. However, in the real-world scenario, It's difficult to obtain actually labeled value for every moment on the disk, which limits the use of supervised learning. In fact, there are still some hairstyle period in the process of experiencing fear, which is reflected in the disk may fail in a very short period. So, the learning effect of the classifier is affected by the misstable sample. Finally, why we use it together? As shown in the figure, by combining the active learning and the semi-supervised learnings in different periods, the learner can select the appropriate sample and improve the classification ability. Here we do not emphasize that this combination is the best method, but just give an idea that can just replace supervised learning in distant field prediction. Figure shows the architecture of ASLDP. There are two main parts, active learners and semi-supervised learners. When these processes are complete, two classifiers with different classification characters are generated to provide real-time prediction service through ensemble learning. During the model training process, we simulate the data generation process according to the real data center scenario. That is, the samples are generated as a string and then put into a pair of windows in coordinate order, including the external windows and the semi-supervised learning window. The sample in the window will end the corresponding learning pool when conditions are met. The learner will select suitable sample to be trained, and then the prediction theory can be provided. Algorithm 1 shows the schedule code on X-learning sample selection. X-learning query strategy in schedule code choose a possibility-based heuristic method that picks up the negative sample with the greatest uncertainty. Algorithm 2 shows our semi-supervised learning process, which is based on semi-supervised learning algorithm called training, but had been adjusted and improved. X-learning can find the most valuable sample and reduce the impact of the redundancy sample on the learner. Semi-supervised learning can improve the performance of the learners by labeling sample with the missing label information. ASLDP can selectively feed the data to the corresponding learning models for training according to the character of the sample in different periods, so that the learner can actually improve its classification ability. The corresponding process is shown in algorithm 3. To validate our ASLDP method, we use the public dataset described earlier. Since it is not emphasizing here that different set of features will affect the prediction result, some commonly used feature selection method will not be used in our model. We only use some commonly used small features. In order to evaluate the performance of the models, the precision, record, F1s, and FAR are used. In addition, I will choose RF, OME, and ORF as baseline. Overall, as shown on the left, ASLDP achieves a high precision, record, and F1 among all compression models and datasets. In the long-term use process, the FDR of ASLDP can also be controlled with the 10%, which is realized online learning and model updating as shown on the right. In summary, our major contributions are as follows. We present the complete design of ASLDPs and evaluate our models on the dataset from real data center. We demonstrated that ASLDP has high flexibility, better online self-learning and self-turning ability, and can overcome the problem of data labeling and the imbalanced dataset. To the best of our knowledge, we piloted the use of X-learning and semi-supervised learning on the distant field prediction. This is very different from the supervised learning method used by most previous research work. By analyzing the character of distant data in different periods, the reason for using X-learning and semi-supervised learning method and the specific implication methods are given. If you have any question or comment, you can contact me. Thank you.